Hello, this is a continuation of our look at types of bonds, and we've already looked at ionic bonds. Remember, ionic bonds, there's a transfer of electrons. So we have a sodium metal with one valence shell electron, and we've already talked about this. And let's say chlorine with 7 valence shell electrons. This one electron is transferred to the chlorine, so the result is we have a sodium plus and a chlorine minus ion staying together. So if we were to draw this, we would see that we would have some cations attached to an anion, right? So the sodium, chlorine, another cation, anion, and it actually forms a crystal structure, which I'm not going to get into the different types of crystal structures, but it forms a crystal structure. So this sodium transferred its electron to the chlorine. So then we have that. There's no free electrons floating around in an ionic compound because all the electrons have been transferred to from the one metal to the non-metal. Okay, but today I want to talk about metallic bonds. Metallic bonds would be bonds that occur between metals. Now, in the purest sense, it's not actually a chemical bond. It's an inter-elemental attraction, but we're going to call it a metallic bond. We're going to call it a bond because it's pretty strong, and there is, energy exchanged. So here, if we have like a chunk of sodium metal, it doesn't get a charge because the electrons haven't gone anywhere. But if we were to illustrate it, we would see that sodium metal has a whole bunch of sodium atoms around it, and there's an electron cloud that keeps this together. So we say that the atoms are in a sea of electrons, and all of these would be cations because their electrons are out here. The valence shell electrons are out here. And this is the reason that sodium metal can conduct electricity. All metals can conduct electricity because it's the atoms make the cations, and then you have all the electrons around it. So all of these would be the same metal. And remember, metals are ductile, meaning that they can be drawn into a wire, and they're also malleable, meaning it can be hammered flat. And the reason for that is this, that these atoms pretty much can move around when their force is exerted. So if force is exerted on this, it can be narrowed, and because remember you have like bazillion atoms here, and it can also be hammered flat, okay? Because it's more like a inter-elemental attraction holding that together. But the two things that I want you to be aware of with metallic bonds is that when we mix different metals together, they're not chemically bonded. They're a mixture, and we call that mixture an alloy. So there are alloys, and alloys are just mixtures of metals. So they can be separated by physical means. It's a physical combination of these because it's not really a chemical bond holding them together. So there's two types of alloys. And the goal of having an alloy makes the metal stronger and cheaper. One or the other or both. Okay, so that's the reason that you would want an alloy, because you get the best properties from both, and together they actually are stronger. The first type of alloy that I want to talk about is an alloy in which all the atoms are the same size. So we could have pure gold here, right? And that pure gold is made up of all these gold atoms. Again, surrounded by the sea of electrons. But this metal would be very soft. In fact, it would almost be unusable because it'd be so soft. So we add other metals that are the same size to it to strengthen it. So what I'm going to do is, since copper with the gold makes a yellow gold. It's very common. I'm just going to put in a few copper atoms in here. Copper is about the same size. So then the copper atoms also contribute electrons to the cloud, but it provides more stability for the gold. So this is called a substitutional alloy because you're substituting a metal with the same size, another metal with the same size in order to enhance the qualities of the alloy. So it's substitutional. There's a lot of examples of substitutional alloys, and you'd have to have two atoms that are about the same size in order to have substitutional alloys. The other type of alloy would be if I have atoms. Let's see this space right here. I can put smaller atoms. I can put smaller atoms in that space, and this creates a very strong alloy. Steel is an example of this. Steel is made out of iron with carbon atoms pounded into the fabric of the metal. I don't know if you've watched Forged in Fire, but they talk about making swords, and the iron has to be forged with the carbon in order to make the steel, because iron by itself rusts and it is weaker, but steel, carbon doesn't rust. So steel, with the carbon put into the fabric of it, actually makes a very strong substance. You know what's stronger than steel, though? Spidey silk. Yeah, spider silk is actually stronger than steel. They're thinking about applications, because if you could have something that's that light, but stronger than steel, imagine, bulletproof vests and stuff made out of it. So this is called an interstitial alloy. Interstitial alloy. It has inter areas, the inter and the small areas. It has the smaller atoms in there. So this also makes a very strong metal. So the two types of alloys are interstitial and substitutional. And the reason that they use different types of metals within the metal is to make it stronger, and sometimes it can make it cheaper. Okay? So I hope this helps. This is it for metallic bonds. There's nothing much more here, and I'm not going to go through the crystal structure or the geometries of what the crystals become, but I do want you to understand the differences and the type of bonding that's going on. Again, it's not a chemical bond really. It's more of an intermolecular bond, but we classify it as a chemical bond because we know the three. Ionic is metals with nonmetals. Metallic is metal and with metal, and then covalent is nonmetal with nonmetal. So it makes a nice, complete little package there. All right. Well, have a great day. I shall see you in class.